Yeah, good morning everyone. We'll get started with today's class. Uh, just a word of reminder to the MTech students. I hope some of your classmates who have joined more recently, they are aware of the class link and also they are aware of the Teams group. So if they have not yet joined the Teams group or if they are not aware of the class link, please make sure that you circulate the link. I think Kshitij had put it in the group. Please ask them to join the WhatsApp group as well, especially the students who joined, I think, in last week. Okay. All right. So let's get started with today's class. So far what we have seen in the class is basically that we looked at the MOS device and we looked at how it is, how it operates, the different regions of operation. We looked at the non-idealities in a MOS device, basically the channel length modulation and other effects, right? And we also looked at, layout in one of the previous classes. We looked at resistors and capacitors, how they are formed in a typical CMOS process. And so all these things we have seen. Now, today we are going to look at small signal operation. Okay. Now, I am pretty sure that all of you have come across small signal models and small signal operation in your, for the BTech students, you have already learned it in your analog electronics class. For the MTech students, I'm pretty sure you have done it in your BTech as well. Nevertheless, I'll just have a quick run through the concepts. I'll just run through the concepts very quickly. In case you have any doubts, in case you want me to elaborate on any aspect of it, please do let me know. Okay. All right. So now, when we look at, let's say, the drain current versus the VGS, right? The ID VGS plot. So we know that this follows you have the quadratic equation, right? It's called as the square law equation. ID is given by mu n Cox by 2 W by L VGS minus VTH the whole square, right? Now this is what is called as the typical square law equation. I also mentioned that velocity saturation changes this exponent of 2 to something which is closer to 1. Okay, some textbooks may say it is to the power of some alpha and so on. So there are different ways by which you can model it and things like that, right? Now, inherently, this equation, the relationship between the voltage and the current is a nonlinear relationship. Right? So that is something that we all can agree. Although this is a very simplistic equation, we have already seen that here it is exponential in nature, here it is quadratic in nature, and here it becomes more linear in nature. It's not exactly linear, it is VGS minus VTS to the power of some alpha, which is more close to 1 rather than 2. All right. Now, so let me just say to the power of alpha, right? Now, this is basically your moderate inversion region, the strong inversion region, and the weak inversion region. Now, here, if you see, so basically this IDVGS characteristics is a highly nonlinear characteristics, right? It is not by any means linear. But if you take, let's say, a fixed point, let's say you take a bias point like this, let's say this is V naught, and then you give a small sinusoidal signal, let's say this is your time axis, right? And let's say you give a small sinusoidal signal which is like this. Let's say, for example, right now it is a 1 millivolt sinusoidal signal. Okay, so the input V in can be written as V naught plus some A times sine omega t, where A in this case is 1 millivolt. Now what happens is, this nonlinear device, when you give a very small signal as your input around a certain bias point, now what happens is, if you kind of zoom in to this region, kind of zoom it in, it's kind of almost linear. You can draw a tangent to this particular thing. Okay, let's just say, just slightly curves and so on. So if you take that small region and blow it up, right, you can approximate it as a linear thing. You can draw a tangent and this tangent has a certain slope. right? So what happens is a sinusoidal signal or some kind of a time domain variation in the signal happening at the input between the gate and the source. So basically we are talking about a device which is like this. Let's say you connect V in like this. Now we are talking about the ID which is flowing here. Now this ID, the output current, let's just call it as I naught, to can be written as a certain DC current which is already flowing. Okay, let's call this as IDC, right? A certain DC current which is already flowing plus the behavior of the sinusoidal voltage variation at the gate translates to a linear sinusoidal variation in the output current. So it is some factor, let's call it as K times this A sine omega t. So what has happened is you took a device which is inherently nonlinear, and then what did was you biased it at a certain point. When you say bias it is biased with a certain VGS, and that VGS is going to set up a certain DC current which is called as IDC. And around that V naught, which is your bias point, you are giving a certain AC signal. Now what happens is this nonlinear device in the vicinity of your bias point, because it's a very small signal variation, right? The transfer function becomes linear or can be approximated to be a linear transfer function. And now this factor, which is going to be, which is relates, this voltage quantity to the current, basically is called as the transconductance. Let's call it as GM. This is what is called as the transconductance. All right. Now, what is transconductance? So basically, your let's take an example so that we understand it well, right? So let's call this as your V in, and let's call this as your I out. Okay. Now V in, let's say it is 0.5 volt plus, let's say 5 millivolt sine 2 pi, let's say 2 kilohertz 2000 T. All right. Now this is how your signal is going to be. Please note that if your bias point, if you give a DC of 0, this is a mistake a lot of students do when they start simulating, right? When you give a DC bias point of 0, then there is no DC current which is flowing and you're literally sitting in this region. Understood? So here there is no DC current which is flowing. If at all something is flowing, it's literally in the order of some nanoamps, which doesn't do anything. Okay. Now you need to bias the transistor, and around that bias point you give your AC signal. Okay. All right. Now what happens to I out? Now first of all, there is the IDC component and the IAC component. Notice that I'm just using capital and small letters just to create the difference. Now IDC can be easily written as mu n C ox by 2 W over L 0.5 volt minus, let's say the threshold voltage is some 400 millivolt. So you have 0.5 minus 0.4 into to the whole square. Okay. Of course, I'm not including the channel length modulation effect here, because for these kinds of calculation, if you start doing that, it becomes very tedious. Okay. Now this is your DC current. Let's say, for example, in this example, it is going to be some 750 microampere. All right. Now this V in, this I out can be written as 750 microamperes plus GM times 5 into 10 power minus 3 into sine 2 pi 2000 T. All right. Now this GM is basically your transconductance, and it has a unit in terms of ampere per volt or Siemens. Okay. And this is your transconductance. Why is it called as a transconductance? You have voltage variation at the input. So you have 3 terminals in your MOSFET, at least in this example, assuming that the body is connected to ground and the source is also grounded. So the body effect doesn't come into the picture, right? So the voltage variation between 2 terminals of a MOSFET is setting up a current on the third terminal of the MOSFET, right? So you have voltage between gate and source, and that sets up a current through the drain, and that is why it is called as a translate. The impedance or the conductance is translated, okay? And here the units is ampere per volt, because it takes voltage as the input and gives you a current as the output. All right. So this is what is called as transconductance. Now, how much is this transconductance? Okay. Now, if you look at this particular plot, I told you that the slope of this tangent decides the linear response, right? Now, what is the slope of this tangent? Basically, GM, the slope is nothing but dou ID by dou VGS at a given VGS equal to constant, right? Now, why do I write that? Because it is obvious that when you differentiate this curve, it's going to have different slopes at different points, right? So, for example, if I were to, bias it here, the slope is going to be like this. Now, if I'm going to bias it here, my slope is going to be like this, right? If I'm biasing it here, my slope will be different, okay? So, every point will have a little different, every bias point will have a different slope, right? So, if we differentiate this particular curve, what do we get, right? Let's say I is mu n C ox by 2 W over L VGS minus VTH the whole square. Now dou ID by dou VGS, what will you get? Now mu n C ox W by L, these are all constants. So first you basically, the 2 and 2 cancels out, you get mu n C ox W over L VGS minus VTH. Okay. Now this is one expression for GM. All right. Now, you can kind of write this in slightly different ways. You can say, okay, this is very similar to my, ID equation. So I can say, I put the factor 2 times ID divided by VGS minus VTH. This is also equivalent, right? The second expression and the first expression are equivalent because ID is this one, multiply by 2, divide by VGS minus VT, you get GM, right? So this is another way to express. There is also another way, you can substitute it with ID and then you can write it as root of 2 times ID mu n C ox W over L, okay? Now again, this is also similar, 2 times ID will give you mu n C ox W over L VGS minus VTH the whole square, right? You take root, you get, under root of mu n C ox W over L. So you multiply with that and put the whole root. Okay. Now these three are the expressions for GM. All right. Now the first thing that we notice here is that your GM depends on, what are the things that it depends on? First of all, it depends on your W by ratio. For a given process, your mu n C ox and all is constant, right? Your VTH is also constant. You don't have any control over it. In fact, as a designer, the things that affect GM, as a designer, you have control over first and foremost the W by L ratio, right? So you change the W by L ratio. Okay, I skipped one page. Okay, right. So W by L ratio, right? Now, what is the relationship between GM and W by L ratio? So if you keep other things constant, right, and you just scale W by L, right, you keep VGS equal to constant, and you just scale W by L, what will happen? GM becomes proportional to W by L ratio when VGS is constant, right? Now, VGS is another thing. What do you see? What else can you say? When you keep W by L ratio constant, GM becomes proportional to VGS minus VTH, right? Now, what else do you see here? If you keep current constant, what happens? GM becomes inversely proportional to VGS minus VTH. So that's the interesting factor over this one. So this becomes VGS minus VTH when ID is constant. All right. Same way, GM is proportional to root of W by L if you keep when ID is constant. And finally, we can say that if you keep everything else the same, GM is proportional to, like if you keep W by VGS minus VTH the same, GM becomes proportional to ID if is constant, or GM becomes proportional to root of ID when W by L is constant. All right. Now these are all very important relationships which help us to understand how does GM vary. Now what we will see is through the rest of this course, we will be heavily depending upon this parameter GM. Okay. The transconductance of this MOSFET is what is going to kind of set a lot of things in your design, be it the design of a simple amplifier or an operation OTA or an op amp or whatever you do, right? GM is one of the most crucial parameters, and you must know how it varies with different parameters. For example, you might bias the transistor with a certain constant amount of current. Then what happens? As you reduce V minus VT, your GM will increase. Okay. Now these relationships are something that you need to keep in mind. So for example, if you keep the VGS as constant and you just increase your ID, then GM becomes proportional to ID. But if you fix your W by L and you try to increase ID, GM will increase only by square root of ID. So keep these three equations in mind. You should kind of have it in memory, or at least be able to write all three of them. So once you start working with it, you will kind of understand. So that, like, when you want to increase or decrease your GM, in fact, what will happen is when we start designing amplifiers, we'll be looking at, okay, I need to increase my GM to increase my gain, or you will say, okay, I want to increase my GM in order to increase my bandwidth. Okay, or you may say, okay, I want to reduce my GM and save current or save power. Or you might come and say, okay, I want to keep my power constant, which means what? You want to keep ID constant, right? While keeping power constant, you want to increase your GM. Then what will you do, right? So, or here again, you have two choices. You might say, okay, I don't want to change my bias point. I only have flexibility with my W by L ratio. Then what will you do? How does GM change? So these relationships you must always keep in mind. Okay. So these are all the ways by which GM varies, and these three equations are quite important. Now, so in this case, what shall we say? Okay, in the example that I took here, right? So I took ID equal to the example. I had taken ID equal to, how much did I take? 750 microampere, right? Okay. And what else did we take? So I didn't give you any other parameters, right? Okay. Let us say VGS, VGS I have given. VGS is 0.5, VTH is 0.4. So what will be your GM? VGS is 0.5, VTH is 0.4, right? Now what will be your GM? You can use any one of the three expressions. With the data that you have, the second expression is what you can easily use. So GM is given by 2 times ID by VGS minus VTH, right? So what does this turn out to be? It's 1.5 milliampere divided by 100 millivolt, right? So it becomes what? 1.5 divided by 100, 0.015 Siemens, right? Or in other words, this is 15 millisiemens. All right. Am I right? Yeah. So your GM, so typically in MOSFET, you basically kind of have GM in the range of millisiemens or microsiemens and hundreds of microsiemens or few millisiemens and so on. Okay. All right. So suppose now I want to increase my GM. What will I do? Either I can go and increase my current. Now, how will I increase my current? So let me put the scenario here, right? My input is fixed at 0.5 plus some VAC, right? So I don't have any control over my VGS here. Okay. But what do I have control over? I can control the current. How can I control the current? I can control the current by scaling the W by L ratio. So for example, if you look at these three expressions, your VGS is fixed. What you can do is just scale up your W by L. Scaling up your W by L automatically increases your current as well. Okay. So it is not that these expressions are all independent of each other. It is just like, you know, you have two different parameters in place. So here WL and VGS, ID VGS, ID WL. So three combinations are given. If something is fixed, you can use the other parameter. Okay. Now here in this case, if GM needs to be increased, what you can do is increase your W by L ratio. So if you increase your W by L ratio, your GM will increase and your ID will also correspondingly increase. Alright. Okay. So now let us build our small signal model. So this is something that I believe most of you would have studied, but if not, we can, we'll go through it. So if you take a device, right? So let's say this is our gate terminal. Let's call this as our drain terminal. This is, let's say, our source terminal. Okay. Now, for a low frequency small signal model, so this is what is called as a small signal model of a MOSFET. So we will be working very heavily with all these small signal models. So I want you to, make sure that you understand these things, right? So between the gate and the source, for a low frequency model, literally there is nothing. It's an open circuit. Okay. So we'll just leave gate and source open. Now what do we have? We have some small VGS here. Now, what is a small signal model? I'm sure all of you have studied it earlier, but let me just recap. Small signal model deals only with small signals, right? In order to do this, you set all DC to 0, right? Your small signal model does not account for your DC, okay? Now, again, let me tell you one more thing. This parameter GM is a small signal parameter, all right? And, okay, let me write it here. GM is a small signal parameter. Now, sometimes I have seen students writing in exams where, if you want to find out the DC current, they will use GM. Okay, that is wrong. For example, if I have given a certain VGS and some VTH and some W by L ratio, you do not use this first expression to find out your current. Okay, find out your current or your, some people what they will do is, like, if I have given VGS minus VTH, let's say in this case it was 0.5, this is 0.4, and W by L ratio is also given. Now, what they will do is, to find out current, they'll say ID is equal to GM times VGS, which is, they will write like this. So they'll say, okay, GM was some 15 millisiemens multiplied by 500 millivolt. This is my DC current. IDC is this much. This is completely wrong. Okay. I have seen students write like this. Please be very clear in your mind. Okay. That's why I took this example also. There is a DC part and there is an AC part. Okay. Like how I wrote this I out expression also. The DC current is 750 microamperes, and on top of that you have a time varying AC signal. Okay. And this GM applies only for the small signal. Okay, please don't make that mistake. Okay, GM is a strictly small signal parameter. It is not a large signal parameter. Okay, so if you want to find your DC current, you have to use the quadratic equation or the square law equation to find out your DC current. So don't get confused between the two things. If you talk about any voltage, any current in a MOSFET, it has two components. It has a DC component and it has an AC component. Like how I have shown here, the V in has a DC component and an AC component. The I out has a DC component as well as an AC component. Okay, even output voltage, everything will have a DC component and AC component. So don't mix up the two. Don't take a small signal equation and take a small signal parameter and use it for your large signal DC calculations. All right. Okay. Now, having said that, so coming to this model, So here what happens is you have noticed that I have written it as a small letter with small subscripts, which basically means that this is a small signal VGS. Okay. So your actual VGS can be written as V capital GS, which is your DC, plus your small VGS, which is your AC. And in the small signal model, we are talking only about our AC component. Okay, all right. Now, between your drain and source, so what did we see here? This whole concept of GM is that it looks at your VGS and it goes and sets up a certain amount of current between your drain and source. So you can say that we have a current source here whose value is GM times small VGS. Okay, and this is a small signal model. We have already seen the concept of R naught. We can arrive at it at two different ways. One is to say that there are no ideal current sources in the world, and therefore every current source in a practical scenario should have a shunt resistance to it. And the other way to look at it is to look at the output characteristics and then say, okay, if my output characteristics, which is ID versus VDS, it's going to look like this, right? Let's say I have biased it, you have biased it with a certain amount of current, right? This is in saturation. Let's say this is your I naught, or let's say your IDC, right? And let's say you are somewhere here. Now what happens is, as your VGS changes, you slightly move around here and there. Your VDS also changes in this direction. So your VDS, as it changes, basically it is going to move, will have a certain slope, right? Now this is your R naught. Now just to recall, R naught is given by 1 by lambda ID. All right. Now, in the small signal model, there is no DC current, there is no DC voltage. We look at only the AC currents and AC voltages. We set all DC currents and DC voltages to basically, we basically, don't consider DC voltages and DC currents here. Okay. So this is a simple small signal model of your MOSFET. Okay, it has a GM component which converts your small signal input voltage to your small signal current, and there is R naught. Okay, all right. Now, what happens when you add in the capacitances? So this is what is called as the high frequency small signal model, right? So now let's again draw gate. This is our GM VGS R naught. Let's say this is our drain, this is our source, right? Now this was the small signal model, low frequency small signal model. Why is it called as the low frequency small signal model? Because we all know that at low frequencies you kind of assume the capacitors to be pretty much like open circuits, right? And so you don't consider them. Now if you take a device, let's say if you take a MOSFET, what are the capacitances that are there? You have a CGD, you have CGS, CGD, and then you have a, let's say this is your bulk which is connected to ground. So you have a CDB and you have CSB, right? Now, how can you draw these things? So let us say you have, first of all, a gate to source capacitance like this, right? And then you have a gate to drain capacitance like this, right? Now, let's say we have the other terminal. Let's introduce the other terminal, which is the bulk terminal. Let's call this as your bulk terminal or the body terminal. Now, what are the capacitances that you're going to see? You're going to see one capacitance like this, which is your CDB, and you also have a CSB. Okay. In fact, you'll also have one CGB, gate to bulk capacitance, right? All right. Now, this is your high frequency small signal model. Basically, what we did is we took the device and we added all the capacitances that are there. So when you are looking at low frequency analog design, you really don't consider so much of the capacitance. You only look at the output capacitance. Of course, you do look at it for the sake of calculating bandwidth. But in the case of RF circuits, like how some of you students had taken the elective in the previous semester, we consider the CGS, CGD and all these things in a very serious way when you talk about RF circuits, right? Now, but for low frequency circuits, you don't really consider so much when you're calculating DC gain and low frequency gain. Of course, when you want to calculate bandwidth, all these capacitances come into the picture. All right. Okay. So far, any doubts, any questions?
Sir, what was that capacitance on left side,
Sorry,
sir?
this is CGB. Yeah, thank you.
CG.
CGB.
Okay.
Yeah, thanks. All right. Okay. Now there is one more factor. So right now we have talked about the small signal model, low frequency small signal model of the device. We also looked at the high frequency small signal model of the device, right? And but then what happens in some cases, as I mentioned, when you use a cascode, right? Let's say you have two transistors like this. Okay. So yeah, before I go there, let me just take this example. Let's say I have a scenario where my bulk is connected to ground and my source is also connected to ground. Now what happens to my high frequency small signal model? What are the things do you think will come out of the picture? My source and bulk are tied together to ground.
So this bulk
So it means source and potential. Then
Yeah, source and bulk are at the same potential then.
so we can collapse this CDB and CSP and CGB into this into this capacitors like CGS.
No,
Directly.
you can't do that. You're kind of getting close, but the exact answer is not right.
So the CSB
Yeah,
is
CSB is
useless.
useless, right? Now your source and bulk are at the same potential, so which means that source and bulk are shorted together, right? So CSB is shorted out, so CSB is not in the picture. Correct, very good. Then, so let us say this is our
C
gate, this is our drain, and this is our source and the bulk, right? So what happens? You basically have your GMVGS here, you have your R naught, so you have your CDB coming like this, right? So the CDB comes between the drain and the source, or drain and ground in this case. Same thing, CGB comes in shunt with CGS, right? So this becomes CGS plus CGB. This becomes CDB. Okay. So in many cases you will encounter like this, right? So CSB does not come into the picture at all. All right. Okay. Now let us say what happens in the case where you have two transistors stacked on top of each other. Let's say in a cascode configuration, right? Let's say the bulk is connected to ground. This bulk is also connected to ground. All right. Now M1 we already saw the small signal equivalent circuit. Now for M2 what will happen? We have already, I mean, we drew this one. So let's first draw the low frequency small signal model, right? So let's say this is our gate, this is our drain, source, and this is our bulk. This is GM VGS, this is VGS, R naught. Let's not talk about capacitance for now. Okay, let us talk about what happens because of a certain VSB, or let's call it as VBS. Okay. Now again, when I talk about VBS here, we are not talking about the large signal VBS. So that is, what is large signal VBS? Let's say I am not giving any AC signal, right? For a large signal or DC analysis, what do? Set AC source to 0, right? You set the AC source to 0. So if I were to use the previous thing, you just have 0.5 volt here. Let's say, this is connected to some load, and then let's say this has a certain VDS and this has a certain VDS. This has a certain VGS. This is connected to some VB1, right? Now what happens? Let's say this potential is at Vx, all right? Vx is the potential of the source, okay? Vx is source potential of M2, okay? Now, what is your VBS? Your capital VBS, which is your DC voltage, is basically what? 0 minus Vx, which is minus Vx, right? This is your DC bulk to source potential, right? Now let us add our AC signal. Okay. So for example, maybe let me go to the next slide so that I'll just redraw it. So let me take one very simple example. Let's say this is again at 0.5 volt, right? Let us assume that this particular voltage is basically going to be at 0.3 volt. All right. And your bulk here is basically grounded. All right. So let us say this is at some, for example, if you keep the same VGS, this is going to be 0.8 volt, which means the VGS for this is also the same. All right. I'm just taking an example. It need not be the same. You can have different VGS also. All right. Let's say we have something like this. Now your capital VBS is what? Minus 0.3 volt. Your bulk to source voltage is minus 0.3 volt. Now, if you add an AC signal, okay, now let us say this becomes, this plus some, 5 millivolt sine omega t, right? Now, this is going to set up some AC current, right? And therefore, this particular voltage will also start changing, right? So, this 0.3 will change with plus some factor with, of 5 millivolt into sine omega t. So, some factor, all right. In fact, it will be inverse in nature, or rather k, if you write plus k will be negative, all right. That of course, because common source response here. So now whatever it is, there is a small change here. In fact, what will happen is that if you try to plot it, this Vx node will be at 0.3 volt, and it will move around like this, right? Now this variation is basically your small VBS, right? So Vx can be written as capital VBS plus small VBS. Now the question that we are trying to address in the small signal model is the small VBS, how does it change your AC performance? Okay. Now your capital VBS is already going to change your threshold voltage and other things, but all put together, right? Because of capital VBS and small VBS, how does this whole thing change? Okay. So now, how do we understand? So if you look at this particular small signal model, yeah.
Sir, when you're writing this Vx equal to VBS plus VBS, should it be minus something? Minus of VBS plus small VBS?
Yes, of course, but like, depending on, so you're saying because it is 180-degree out of phase, that's what you're asking, right?
Sir, like VBS is body to
Right.
source, right? And Vx is the source potential.
Okay, yeah, you're right. Okay, let's say this is minus Vx. Yeah, you're right, correct. Okay, minus Vx is this particular thing. Okay, yeah, thanks. So now, if you look at this particular device and kind of just observe it carefully. So here, what does this bulk to source voltage do to our transistor? What is the effect? In a large signal sense, you can talk about in a large signal sense what happens.
threshold voltage will increase.
Threshold voltage will
Threshold
change,
voltage, sir.
okay, depending on which direction your bulk to source voltage is going to go, right? So this VSB, right? So the DC component of VBS is going to give you a fixed difference in threshold voltage, and as you have an AC component on your VBS, the threshold voltage is going to vary along with the signal. Understood? The 0.3 volt here, or the VBS of minus 0.3 volt, produces a fixed change in your threshold voltage, and along with that you have an AC component, so which means the threshold voltage of this M2 transistor is going to vary along the signal, or the threshold voltage of this particular VBS of this particular transistor M2 is going to be time variant, or rather it's going to change with time, change with signal. Okay. Now, if you look at the expression for, let's say, normal GM, you see that the normal GM kind of has VTH in its expressions. If you look at these things, right, GM is dependent on this threshold voltage also. It is VGS minus VTH. So what does it mean? It means that as your threshold voltage changes, right, your GM is also going to change. Okay. So the way we understand it, the way it is modeled, is to say that what we are going to do, and also there is one more thing. If you see here, you can see that this is, you know, the VBS is in this particular polarity. So the way it is modeled is to say that we are going to model this as one more additional component. Okay, let me draw it here. Let's say this is your source. This is GM VGS. Now this GM itself is going to change based on the signal, or in other words, the current drawn through the drain, this small ID, is going to change based on the signal. So what we put is, we introduce one more parameter called as GMB, and this is going to be proportional to VBS. Of course, you have R0 here, okay? And you say, okay, we have a certain, let's say this is your VGS, and you have the bulk terminal. This is going to be your small VBS, okay? Now, what is this quantity GMB? Okay, so GMB is, in other words, like you can also think of it, like if you recall the discussion that we had in one of the previous classes, we saw that, you know, the bulk is like, you know, some people call it as the back gate, or it also kind of acts as a second gate, right? Because there is your main gate, and then you have your bulk, which is going to control how much, you know, electrons are going to move towards your gate or not. So it's like one additional gate that you have. So it is almost like a secondary gate that you have. So GMB is defined as dou ID by dou VBS. All right. Now, if you write this expression, so we know the ID expression. So if you differentiate the ID expression, you get mu n Cox W by L VGS minus VTH. Now here the only parameter that is going to change with respect to VBS is the threshold voltage. So you differentiate that. So it becomes dou VTH minus dou VTH by dou VBS. All right. So your GMB becomes this. All right. Now, again, the relationship is quite non-linear between the bulk to source voltage and the current. Again, we use the same concept that, you know, although it is a non-linear transfer function, because you remember the VTH expression that we wrote, the VTH expression was a little, you know, complicated expression which had some, you know, two under root of terms, right? So it is definitely a non-linear relation, right? So let me just write it for the sake of completeness. VTH is given by VTH naught plus some gamma times root of 2 phi f plus VSB minus root of mod, you know, 2 phi f. This was the expression that we saw. And what we now need to do is to differentiate this expression with respect to VBS. Okay. Differentiate this with respect to VBS. So it turns out that dou VTH by dou VBS, VBS is nothing but dou minus dou VTH by dou VSB, right? You change the subscripts and this becomes minus gamma by 2 phi f plus VSB, the whole to the whole power of minus half. And GMB is what? It is basically nothing but GMB is nothing but what? Mu n Cox W over L VGS minus VTH into minus dou VTH by dou VSB, right? Now, what is this term? This term is nothing but GM, right? So GM into this other term. So GM into, so minus of this one, and therefore you get GM into gamma divided by 2 root of 2 phi f plus VSB. Okay. Now, this entire term is captured as a parameter eta. Okay. Now, eta, so therefore, GM can be written, sorry, GMB can be written as some eta times GM. Okay. And this eta is nothing but GMB by GM, and it is around 0.25. All right. Now, as a circuit engineer, what will you do? You just model this to be a current source in parallel with your GM-VGS, and this is the way that you account for your bulk to source voltage. All right. Okay. So again, bulk to source voltage, its dependence on current is a nonlinear thing, but then we say that when you have a small signal variation, you can draw a tangent there, and we saw what is the slope. We derived the slope here, and we said, we model our transistor to be like this. Okay. So in fact, what you will do is that if you look at even your complete high frequency model with the bulk involved, you have that additional terminal GMB VBS. Sorry, additional current source GMB VBS. So this is your high frequency small signal model, and your low frequency small signal model basically is going to look like this. Okay. Now, obviously, when you have your bulk to source voltage as 0, you don't consider the GMB term. But when you have your bulk to source voltage not being equal to 0, you consider the GMB term as well. All right. So, any doubts, any questions?
Sir, you were telling something about second gate in
Right.
between.
So
What
that
was
is
that,
just
sir?
to say that, if you take your MOSFET, right? I was just trying to justify why we write GMB. I said, like, when you have your bulk, let's say, I think you had pointed out earlier, right? Like this is let's say this is a P plus thing, this is your bulk terminal, right? Now, this bulk potential is going to affect, how much electrons or holes, electrons go here and how much they don't, right? Like, so it is almost like you have a control over the backside of the gate. So here your gate potential is there. Sometimes they call it as the back gate and things like that. Okay, so it is like almost that, you have this channel area, right? Of course, inversion channel happens, but then it is dependent on both these potentials, right? So it is almost to be considered like a kind of a second gate which is there, right? Which is why I was trying to justify why you put two current sources together, GM and GMB. Okay, that
Okay,
was
sir.
the analogy I was trying to have. Okay, all right.
Yes, sir.
Okay, any questions, any doubts? Yeah.
Sir, like in the earlier in this lecture, sir, you were talking about transconductance. So I missed out the part like why is the name trans
Okay.
there? Like conductance is
Right. I was trying to explain that also. No problem. I'll explain it again. So the deal is here. Okay. So if you take the MOSFET, let's say as a 3-terminal device, assuming that your bulk is also grounded here, you are setting up a voltage between two terminals of the MOSFET, which is the gate and the source. but this controls the current through a different terminal of the device, which are drain. Okay. If you're talking about the current through the same terminal or one of these two terminals across which the device is connected, then you don't need to use the word trans, right? But here what happens is the voltage is between two terminals and the current which is controlled is through the third terminal of the device, which is why it is called as the trans conductance. The the impedance of the conductance is translated to a different terminal. Yeah.
Okay, sir.
All right. Any other questions, doubts?
VBAC is
Yeah.
sir.
Yeah, tell me. Yeah, I can
Hello.
hear you now. Yeah, go ahead.
Sir, I have a query that VBS is only vary in cascade like connection,
Yes,
as you
yes.
told.
Okay. And it will not be varying if you have a, for
Or,
example, for M1,
or constant.
for M1,
Yes,
there
sir.
is no VBS variation, right? Both bulb sources are shorted together and to ground. So VBS is 0. So I just gave an example of a particular scenario where your bulk is at a different potential. It's not only in cascodes, you will see that there are, certain other circuits also where you have, but mostly in cascodes you do definitely find this.
It means that VBS is only vary in multi-stage transistor. We can say.
Why don't you wait for maybe a few more lectures? Because when we start talking about a common gate amplifier, so there you will see that your input is given to the source, and there you will see GMB coming into the picture, and so on. Okay. So even in a common
Okay,
drain
sir.
amplifier, the output impedance will have 1 over GMB. It will be 1 over GM plus GMB, in fact. Okay. Yeah.
Okay, sir.
So you will understand as the
Sir.
course goes by, you will see. So these are all very fundamental steps, so that if you get a good grasp of them, when we come to all those different circuits, it will become very easy. Yeah, go ahead. Somebody had a question? Yeah.
Yes, sir. Dhruva here. So, when we are operating at
Yeah.
a particular bias point, can we try to define some sort of slew rate for the system, for the whole transistor itself?
Slew rate is there. We look at slew rate for op amps and so on. What do you mean by slew rate here?
Slew rate in the sense the duration until which the linearity is maintained, because when we do the AC analysis, we can see the drop down at a
Right.
particular high
Right.
frequency level, right? Sir?
Okay.
So similarly,
Yeah.
for a large signal, can we define some sort of
Okay.
slew rate?
Actually, I understand what you're trying to say. Let me clarify. So, slew rate is a time domain related parameter. Okay. Now, when you have a very large signal step, for example, when we look at OTAs, and especially when you put OTAs in feedback and try to drive capacitive loads and so on, the current through your OTA or your op amp will limit your this thing. Okay. So, that is slew rate. Now, when you're talking about a large signal being applied to the input, you want to know whether there is a certain range over which this linearity holds good. Is that what you're asking? Like, yeah.
Correct,
Yeah.
sir.
So basically,
Exactly.
as we saw in the RFIC course, so it is a soft non-linearity. So you don't have like dropping off a cliff kind of a response. In fact, for low frequency analog circuits, we
Correct.
define what is called as THD. In RFIC course, we looked at the first order compression, the third order nonlinearity, the 1 dB compression point, the two tone tests, and the intermodulation, IAP3 and things like that. So in low frequency analog circuits, we don't talk about two tone tests and 1 dB compression point. We define what is called as total harmonic distortion. Okay. So
Okay.
basically the same concept, it's just that it is typically expressed as THD. THD comes from the same thing. So yeah, anyway, I will talk about nonlinearity later. But then if you look at this GM, the slope is dou ID by dou VGS, right? Although this is the first order component, you can, if you look at a little larger signal response for your example, if you look at this first curve that I had drawn, right? Now you can express this as a polynomial function. In fact, this is a quadratic equation. Now this quadratic equation basically is the square law equation, which is not very much valid, right? But you know, you can express this as a polynomial. Now once you express it as a polynomial, you have the second order, third order, fourth order, fifth order components and so on, and you define harmonic distortion. So typically in analog circuits, you kind of drive it to such a point till your THD is tolerable. Okay, so depending on the application, your THD that is tolerable will be different. Okay.
Okay,
Yeah.
sir. Got it.
Anyway, so let's conclude the class. But before concluding the class, let me throw a bomb at all of you guys. This equation that we looked at, this ID equation, if you try to extract in modern CMOS processes, if you try to set a value of mu n, Cox, VTH and all that, this equation will not work. Okay. So, so you may ask the question, why did we go through all the pain of looking at it? What works is basically these relationships. Okay. In fact, even the GM equations, these equations do not work directly, but these proportionalities which I wrote, which is why I took the time to go through these, you know, relations, right? These proportionalities. So these kind of work, all right? So if you scale W by L, GM will scale. But all these other parameters, the constants mu and Cox, VTH and all, these all are for modern CMOS processes, the equations are very, very complicated. In fact, the ID equation, if you see, it will come for some 2-3 lines on a printed document. Okay, so it is such a big, complicated, mammoth equation. All right, which is why we depend on simulators for all our IC design work. All right, but what we can do is, of course, we will go through it in the class also. Yeah.
Sir, it's already
Oh, you have
time. We
another
have
class.
another
Okay.
class.
Yeah, we'll conclude here. We will continue in tomorrow's class. Okay. All right. Yeah. Thank you, guys. Have a nice day. Yeah.
Okay, thank you.